a hearty welcome. To the participants, we wish you all the very best. You have done a very good job in your first round of presentations, and it is a tough competition. So we really wish that you will do your best and may the best of you win. I would now like to officially welcome our dear Professor Satish sir, who is actually, as everyone knows, he is the key force, he is the driving force and the brain behind each and every one of these, these great ventures that we take up. And the sir is here to say a few words to address the gathering. I request you, Satish sir, to please say a few words.
Good evening, esteemed colleagues, distinguished members of the evaluation committee, respected chair of the session, and our brilliant finalists. It gives me immense pleasure to welcome you all to the final round evaluation of the Best Paper Presentation Awards of the International Conference of Recent Trends in Statistical Theory and Applications 2025, popularly known as Wsta 2025. The journey began with the conference held from 29 June to 2nd July 2025. Now culminates this evening as we come together to celebrate the research excellence, intellectual rigor, and innovative contributions to the field of statistics and its diverse applications. Today's session represents the final stage of this rigorous evaluation process. Each finalist will present their research once more before our distinguished panel of judges, who will assess their work on multiple dimensions, especially originality, scientific contribution, methodological soundness, and presentation effectiveness. Let us take a moment to appreciate the spirit of this event. It is not merely a competition, but a platform to encourage scholarly excellence, promote meaningful dialogue, and inspire young researchers to advance the frontiers of statistical science. I would like to extend my sincere gratitude to all behind this venture and the esteemed panel of judges for their time and their expertise, and above all, to the participants who have made this session a true celebration of research innovation. To our finalists, congratulations on reaching this stage. Your presence here is a testament to your hard work, creativity, and dedication to the discipline. Regardless of the final outcome, you have already made a mark in this academic journey. With that, I finally declare open the final round evaluation of the Best Paper Presentation Award of WST 2025. I wish all the presenters the very best and look forward to an engaging and insightful session ahead. I invite the panel jury of the members, in particular for sharing the rules anyway, whatever be, and let us we are once again welcoming all of you. I remains here. Thank you. Welcome all. Thank you so much for your support.
Thank you, Professor Satish.
Thank you, Satish sir. So now it is time to introduce our panel of judges. We have with us three eminent statisticians, three stalwarts of the field of statistics, to judge the competition. Professor Loganathan, Professor, Central University, Tamil Nadu, is the convener, and we have two panel members, Professor D.K. Ghosh and Professor Kanchan Jain. Professor D.K. Ghosh is a retired professor and head of the Department of Saurashtra University, and Professor Kanchan Jain is retired professor from Punjab University. Now I would like to request our panel convener, Professor Loganathan sir, to introduce his members once more officially and to declare the rules and regulations of the competition to the participants. Welcome you, Loganathan sir.
Thank you, Dr. Satish Kumar sir. Thank you, Dr. Subhanaya madam, for inviting us to be a part of this WSTA 2025 Best Paper Award program. and it gives me immense pleasure to thank you on my behalf and on behalf of my colleagues, Professor D.K. Goshar and Madam Kanjan Jain, Madam, for inviting us to be the jury, the panel of juries for conducting this Best Paper Award. And as stated by the chairperson at the beginning, each candidate we are given with 9 candidates, shortlisted candidates for final round of the Best Paper Award. There are 3 awards, and each presenter is given with 20 minutes in total. Out of 20 minutes, you please stick on 15 minutes for making presentation and 5 minutes for interaction. So you don't go beyond this. Prepare your mind, set your mind to make your presentation effectively within that 15 minutes, and to enable us to interact with you and the participants to interact with you in the remaining 5 minutes. So for this, my colleagues, Professor D.K. Goshar and Professor Madam Kanjan Jain, Madam, are here with us for conducting this program. And we have been in this team for the past few years. And on behalf of my fellow colleague members of this jury board, we thank the organizers of Wsta, particularly Professor Satish Kumar sir and Madam Subhanayar Madam, for giving me this opportunity. We will try to stick on this time, and we will try to finish everything by 8:45. So, as sir, you have given us the list of candidates and the titles also. And my dear participants, as mentioned by the organizers, each candidate shall make a presentation, and your presentation will be evaluated based on 6 criteria: theoretical and mathematical content with 25 scores, applicability of the problem and illustrative examples 20 scores, clarity of presentation 15, adherence to time 15, clarity in answering questions 15, overall presentability 10. So keeping this in your mind, make your presentation effectively and to secure more scores. Wish you all the best. I wish all the 9 contestants all the best and to achieve success. So, sir, Professor Goshar, Madam Kanjan Jain, Madam, shall we invite the first contestant?
Yes, sir.
Right. So
Thank you, Professor Loganathan.
Thank you, Madam. Thank you,
Introducing
Madam.
us.
It's our pleasure. It is our pleasure. And now the time is 5:36. Our first presenter is John Deep. John Deep Das. John Deep Das. Has he joined?
No, sir. He has not joined.
Okay, right. Then Alicia Matthew.
Is there?
Yes, sir.
Sir, Professor, Madam Jain, Madam,
Yes, sir.
Shall we allow the second candidate, because the first candidate there is no response? Shall we
Yes,
invite
sir.
the second candidate to make the presentation?
Yes, sir.
Yes, sir. Dr. Alicia Matthew, you please share your screen and make the presentation, and switch on your camera also.
He has come, John Deep.
John Deep has come.
Yes, sir.
Wait a minute, Alicia Matthew. John Deep.
Yes, sir.
Yes, he has joined.
John Deep Das. John Deep Das.
He's there.
No response. No,
Yeah, he's there.
He's there.
Take some time.
Am I audible, sir?
Yes. So you are the first candidate.
Yes, sir. Actually,
are you
here heavy rainfall. Heavy rainfall is coming, so some network issue has been happening. So
It's all right.
Sorry,
Are you ready to make your presentation?
yes, sir.
You please start the presentation. 20 minutes for
Okay, sir.
presentation, 15 minutes presentation, 5 minutes interaction. Keep it this mind. And now the time
Okay,
is 5:38 sharply. Alicia Matthew, please, you can present after John Deep Das.
Yes, sir.
So all others can mute your mics. Please, John Deep Das. Your screen is visible. You can start presentation. Jandeep Das,
Yes, sir. My
start.
screen is it visible, sir?
It is
Yes, it
visible.
is visible.
Visible, please.
Okay.
Go ahead.
Okay.
Go ahead.
Okay, sir. Good morning, everyone. Myself, Dr. Jandeep Das, and I am delighted to present my research titled Properties and Applications of a New Alpha-Skew Laplace Distribution. And this research mainly focus on a novel extension of the alpha-skew Laplace distribution aimed at effectively modeling dataset with both unimodal and bimodal characteristics. The proposed distribution is extensively examined, including its moments, momentarity functions, and some other properties. Besides real-life applications, including some real-life patterns are considered, which highlight its superior performance over established model. The new distribution consistently receives lower value attacking gradient function criteria, including its strong model fit for complex datasets. Finally, the likelihood ratio test is also conducted to provide further statistical evidence of its advantages over an estate model. So these are my contents. Introduction. Though normal distribution, or which is also known as quotient distribution, is considered as most widely used continuous probability distribution in many statistical works and is very crucial tool for fundamental data analysis. But when data with asymmetry arises, then normal distribution cannot express the situation wisely. And then to tackle this kind of situation, in 1985, Azalani introduced the path-breaking well-known continuous probability distribution known as skew normal distribution, and this is the PDF of the skew normal distribution, where lambda, one parameter he introduced as a known as the asymmetry parameter, which regulates the asymmetry, and small phi and capital phi are the PDF and CDF of the standard normal distribution respectively. And with this introduction, subsequent research in the literature have been extensively carried out by different researchers into the skew normal distribution. Some significant contributions towards the development of skew normal distribution includes the works of Azalani in 1986, where he discussed some very important properties of the skew normal distribution. And hence in 1986, Azalani and Delavalle in 1996, Azalani and Capitan in 1999, etc. Besides, in 2005, Ariel and Nadaraja presented the skew Laplace distribution by employing the framework of the skew normal model introduced by Azalani. This involves substitution of the CDF and PDF of the standard normal distribution instead of with those of the standard Laplace distribution. So this is the PDF of the skew Laplace distribution. Likewise, the skew logistic distribution, which was also introduced by Wahed and Ali in 2001, follows a skewed model framework based on the skew normal distribution. Besides, in 2009, Nadaraja also discussed some important statistical properties of the skew logistic distribution. In addition to examining different skew distribution capable of fitting unimodal datasets, there are some families of distributions designed specifically for modeling datasets exhibiting bimodal behavior on both symmetric and asymmetric cases. In 2005, Kim introduced a category of two-piece skew normal distribution that extends the skew normal distribution proposed by Azalani in 1985 to accommodate bimodality. On a separate note, in 2010, Elon introduced another innovative distribution family designed to fit both bimodal and unimodal data. This new family of distribution is known as alpha-skew normal distribution, and this is the PDF of the alpha-skew normal distribution. And employing the similar approach, in 2014, Hazarika and Chakraborty introduced the alpha-skew logistic distribution, which is a logistic counterpart of the alpha-skew normal distribution. Similarly, in 2013, Harandi and Alamatas applied the same concept to introduce the alpha-skew Laplace distribution. This is the PDF of the alpha-skew Laplace distribution. Besides all this, Balakrishnan alpha-skew normal distribution by Hazarika and Chakraborty in 2020, Balakrishnan alpha-skew logistic distribution by Chakraborty and Hazarika in 2020, Balakrishnan alpha-skew Laplace distribution by Shah et al. In 2020, generalized Balakrishnan alpha-skew normal distribution, Balakrishnan alpha-skew generalized T distribution, etc. Some other model which should also develop to fitting bimodal data. So, employing a similar approach, in 2017, on the other hand, in 2017, Sarafi et al. Introduced a novel generalization of the alpha-skew normal distribution proposed by Elal Olivero, that is the alpha-skew normal distribution. This generalization encompasses normal distribution, skew normal distribution of Azalani, and alpha skew normal distribution of Ella Olivero in 2010, and normal distribution as two specific cases, terming the generalized alpha skew normal distribution, it proved to be a superior fitting model compared to the alpha skew normal distribution, particularly when dealing with dataset involving up to 2 modes. And this is the PDF of the generalized alpha skew normal distribution. In this study, a new family of skew distribution we have developed to accommodate data with both unimodal and bimodal behavior, employing the mechanism of the generalized alpha skew normal distribution proposed by Sarah et al. In 2017. In this context, the PDF and CDF of the Laplace distribution are employed instead of the standard normal distribution. This results in a new distribution that serves as a generalization of existing families like alpha skew Laplace distribution, skew Laplace distribution, and the Laplace distribution. Additionally, the superiority of the proposed model is assessed by comparing it with some existing submodels found in the extensive literature employing two real-life datasets. So this is the new family of distribution given in equation 2. And this new family of distribution is named as generalized alpha skew Laplace distribution. And C is the normalizing constant here, calculated as 2 into 1 plus alpha squared minus alpha lambda 2 plus lambda by 1 plus lambda whole square. And now, using the concept of Gupta and Huang provided in 2002, the PDF of the generalized alpha skew Laplace distribution can be also written by this using the sine function. These are some special cases. If we consider alpha equal to 0, then we obtain a skew Laplace distribution of RL and others are introduced in 2005. If we consider lambda equal to 0, then the generalized alpha skew Laplace distribution reduced to alpha skew Laplace distribution of Harandi and Alamitas in 2013. If we consider alpha and lambda both equal to 0, then the generalized alpha skew Laplace distribution reduced to standard Laplace distribution. And if x is a random variable that follows generalized alpha skew Laplace distribution with parameter alpha and lambda, then minus x will follow generalized alpha skew Laplace distribution with parameter minus alpha and minus lambda. These are the plots of the generalized alpha skew Laplace distribution for some different parameter value. And from this plot, we can observe that the distribution can have at most 2 modes, and also sometimes it may behave as unimodal distribution. So then we have computed some important statistical properties of the induced distribution, that is the generalized alpha skew Laplace distribution. Firstly, we calculated the cumulative distribution function, and this is the cumulative distribution function. These are the plots of the cumulative distribution function for different parameter values. This is the nth order moment of the generalized alpha skew Laplace distribution. And we consider n equal to 1, 2, 3, and 4 and obtain first four raw moments of the generalized alpha skew Laplace distribution. And these are the expressions. This is the moment generating function of the generalized alpha skew Laplace distribution. And if we consider it instead of t in the equation of moment generating function, then obviously characteristics function of the generalized alpha skew Laplace distribution is obtained. And considering logarithm on the both sides of the equation of moment generating function, we obtain the cumulative generating function of the generalized alpha skew Laplace distribution. This is the mean deviation of the generalized alpha skew Laplace distribution, and this is the mean deviation about mean given in the equation. And if we consider, if we replace mu of the equation by median capital M, then we obtain the mean deviation about the median of the generalized alpha skew Laplace distribution. This is one characterization results if we consider one variable, that is W, which follows alpha skew Laplace distribution with parameter alpha, and another variable Z, which follows standard Laplace distribution, and both are independent, then the conditional distribution of W will follow generalized alpha skew Laplace distribution, that is our new distribution. And we can use this these results to generate data from the new distribution using the acceptance rejection algorithm, and these are the algorithm. And then we come to the parameter extension part. Firstly, we extend the location and scale of the new distribution, and this is the location and scale extended distribution, where mu is the location parameter and beta is the scale parameter. Then this is the log likelihood function. We go to the maximum likelihood estimation, and this is the log likelihood function. And differentiating this function, we obtain the log likelihood equations, and equating these, we can obtain the estimates for the new distribution. But we can observe that these equations are not in explicit form. So numerical approximation method is employed here using R software to obtain the MLE for the parameters, optimizing the set of parameters. Then a simulation study is conducted to assess how well the maximum likelihood estimates perform in estimating the parameters of the model. The acceptance rejection algorithm that was discussed in earlier sections is employed here for generating a set of random variables. The process is replicated 1000 times along with the 3 different generated samples of size n equal to 100, 300, and 500. And finally, the MLAs are estimated for each generated sample using the GenSA package in our software. The estimated steps.
You have 3
Yes,
more
sir.
minutes. 3 minutes. You have 3
Okay, sir.
minutes.
Okay, sir. The estimated statistics are presented in terms of bias and MSE, and these are our formula. And we have presented here the simulation results. This is the table 2, and this is the table 3. This is the table 3. And from this table, it can be observed that as the sample size increases, bias and MSE decreases, which confirms the asymptotic consistency of the MLEs. Then I come to the last part, that is the real-life applications. And in this section, to check the adaptability, usefulness, and flexibility of the new model over some other counterpart like Laplace, skew Laplace, alpha skew Laplace, alpha skew normal, alpha skew logistic, etc. We use 2 data sets, and GenSA package within the R software is used to fit the model. Besides, to assess and compare the models, some model selection criteria like AIC and BIC are used. So this is the application 1 for which we use the WCC datasets, and information for the datasets are given here. And we have presented here this table 4, and from this table, we can observe that the value of AIC and BIC of the generalized alpha skew Laplace distribution that is presented in the last row is lower than that of the other distribution under consideration. So it is possible to draw the conclusion that the generalized alpha skew Laplace distribution is another good alternative for modeling bimodal datasets. From the graph also, we can observe that the new distribution possess bimodal shape, from which also we can draw the same conclusion. And this is the dataset 2, for which we consider the failure times of aircraft windshield datasets. And this is the table. From the last row of this table also, we can observe that the AIC and BIC of generalized alpha skew Laplace distribution are less than that of the value of other distribution under consideration. And from the figure also, we can observe that the new distribution provides good fit. So from this illustration, we can conclude that the generalized alpha skew Laplace distribution is better fitted for modeling bimodal datasets. Then this is the hypothesis testing. We consider the likelihood ratio test to discriminate between some nested model. Here we consider the skew Laplace distribution, alpha skew Laplace distribution, and Laplace distribution. And for all the 2 data set, we can observe that the value of the likelihood ratio test statistics is greater than that of the obtained tabulated critical value at 5% level of significance, which can be from which we can state that the collected data originates from the generalized alpha skew Laplace distribution. Then conclusions: this research presents a generalized alpha skew Laplace distribution as a significant contribution to the dominant of skew probability distribution, capable of addressing the limitations of existing models by effectively capturing both unimodal and bimodal characteristics. The theoretical derivation of its properties reveals in advanced structure.
Is the last slide? John,
yes, sir, it is. Yes, it is.
Your time is over.
Okay.
So this is the last slide, right?
Yes, sir. Please.
Okay, fine, very good. Okay, right. Congratulations, Jandeep Das, for making a very new distribution for studying a new distribution. And the session is open. First, our jury members will interact with you. Professor Ghosh, Professor Madam Kacha Jain, Professor Ghosh.
Yes.
Okay. So my question is that In 2020, in Indian Journal of Agricultural Statistics, with the same
Yes,
name, a new alpha square Laplace distribution by Hazarika Chakravarti have published. And you are also publishing the same name. They found the bias and mean square error. They compared the AIC and BIC, and you have done the same thing. Then what is the difference? When name the paper, title of the paper, you also say.
No, sir. They sir introduced alpha skew Laplace distribution, and I introduced a generalized alpha skew Laplace distribution. That is like sir. Alpha skew normal distribution, and one extension of alpha skew normal distribution is generalized alpha skew normal distribution with one additional parameter.
The second question, in table 5, I found as the distribution is changes, your mu and beta are irregular. There is no trend of mu and beta. Why it is so? Table 5.
This one, sir.
Yeah. See, mu and beta, as the distribution changes, the mu and beta, there is no any regularity. Whereas in earlier table, that mu and beta has some trend. Why it is
This
so?
one, sir.
Yeah, here is some trend. But there is no trend like that.
Yes, sir.
Why the reason?
Yes, sir. I need to check about that, sir. I need to check, sir. Please data fitting, sending the data with more data. I need to check, then I can come to the conclusion.
Thank you.
Well, madam.
Thank you, sir.
Yes. You say you will check for more data, but this is a practical illustration.
Yes, ma'am.
Here you will have data on 84 aircrafts windshields only.
Yes.
So you can't include more data in this.
No, ma'am. Actually, data set I can check with another data set. Another data set.
Yeah. Yes, you can take another data set.
Yes.
Like
Yes,
Professor Ghosh questioned you about new class.
Yes,
Why don't you use the word generalized in title of the paper?
Ma'am, actually, in this paper, we follow the mechanism of generalized alpha skew normal distribution, which was actually one generalization of the alpha skew normal distribution introduced in 2010. So we use the same mechanism for the Laplace distribution. That was Sir has already told.
Can you go back to your title? First slide.
Yes, ma'am. Sure, ma'am.
Is this generalized in distribution introduced by you? No, first slide, it's okay. Here you are saying a new generalization, no? First slide says of a new alpha skewed Laplace distribution.
Yes, ma'am.
So why don't you use the word generalized here?
Okay, ma'am, sure. I will use that word next time.
So do you take the credit for introducing generalized alpha skew Laplace?
Yes, ma'am, obviously.
So what was there in 2010? Like you were talking of some distribution.
Ma'am, this was the distribution, alpha skew normal distribution, that was introduced in 2010.
Okay. So you have generalized it.
No, ma'am, I have generalized this distribution. This was ma'am alpha skew normal distribution.
Okay.
And this was ma'am alpha skew Laplace distribution, and so I have generalized this one.
You have generalized this distribution.
Yes, ma'am.
Okay. Is it published or about to be published?
Yes, ma'am, it is published.
Okay, thank you.
Welcome.
Thank you, ma'am.
John Devdas, how do you diagnose? How will you diagnose whether your data fits to deserves to receive the application of this new alpha skew Laplace distribution? How will you diagnose it?
Sorry, sir.
When you are given with the practical data, real data, how will you
Yes,
know
yes, sir.
that that data deserves the application of your distribution?
Sir, we check some in some existing literature, previous paper, and we take the data that is used for some bimodal development of skew distribution, and these two data were used to develop some bimodal distribution previously, and
The
so
thing
we
is,
consider these two
do
data.
you have
Yes.
do you have any properties kind of a thing the data should have for the receiving the application of this new type of distribution? That is what I am asking about. If anyone wants to apply your the distribution to their data, how will they know that their data deserves the application of your distribution?
Yes, sir.
Okay, no answer. Very good. Thank you, John Devdas. You can
Hello, hello,
and
Dr.
you,
Loganathan.
sir.
Myself, Dr. Shubhanga Datta from Manit Bhopal. So, may I ask you, John Deep any queries regarding this problem? Actually, may I ask?
Sir, we are given with 20 minutes time for each candidate, and we are asked to work with
I
the
have
time
one.
zone.
I have one query regarding that.
Please,
Yes, yes.
make it faster.
Yeah, John Deep, I found that you got the distribution, which is the bimodal distribution, right? So when you were discussing about the MLE, so did you discuss about? Did you mention about the local maximum likelihood or the global maximum likelihood? I got confused regarding that actually, because it's bimodal distribution. It's not a single mode. So
Good question.
Which one?
yeah,
No, sir is asking that it is a bimodal distribution.
Yeah.
Whether your maximum likelihood estimate is global
Actually,
maximum.
time is taking
or
more.
maximum.
Time is taking more.
Okay.
Yes, sir.
Manage the time.
Okay. Sorry, sir. It's fine.
Well,
Okay.
well, Jagdeep Das, thank you. You please close your screen, and you have not shown your face. Well, let us call the next candidate, sir. Dr. Alicia Matthew.
Yes, sir.
Jagdeep Das, you close your screen.
Okay,
Alicia
okay, sir.
Matthew, fast to share your screen and switch on your camera.
Yes, sir. Sir, I hope my screen is visible.
Yes, it is visible. Now the time is from the time. 15 minutes for presentation. Make it fast.
Good evening, everyone. I'm Alicia Matthew, PhD scholar in the Department of Statistics, Bharatiyar University, under the guidance of Dr. K.M. Shaktivel, Professor, Department of Statistics, Bharatiyar University. Today, I will be presenting my work on modeling geological orientation using a new circular probability distribution. Here is an overview of my presentation. I will begin with a brief introduction to circular data and the motivation behind developing the new model. Then I'll describe the proposed distribution, followed by some key mathematical properties, parameter estimation, and application to real data, and conclusion, and then I'll end with the references. Introduction. The world around us is full of patterns that repeat in cycles, from the direction of the wind to the daily rhythm of time itself. And these characteristics are not linear but circular, requiring specialized methods of analysis. Observations recorded as directions are known as directional data. In 2 dimensions, this is specifically termed as circular data, since each observation can be represented as a point on the circumference of a unit circle, and it can be measured as an angle from a fixed reference point and direction of rotation, which could be clockwise or anti-clockwise. And these directional data are widely used in various scientific disciplines. And drawing meaningful statistical inferences from any data set requires choosing a probability distribution that best captures its underlying characteristics. In the case of circular data, several techniques have been developed to derive circular models from existing linear distributions. And one of the most notable approaches was introduced by Lawai, who proposed wrapping a linear distribution around the circumference of a unit circle to form a circular counterpart. Because 0 degree and 360 degree denote the same direction, conventional statistical measures such as the mean and variance cannot be applied directly here. Like, for instance, the average of 2 degree and 358 degree is certainly not 180 degree. Therefore, the analysis of angular or directional data, it demands a specialized statistical methods which will respect the circular nature of the measurements. And since there are no natural zero direction, any numerical representation of direction depends on an arbitrary choice of reference. So it is important that statistical analysis and subsequent conclusions are invariant to this arbitrary choice of zero direction. The position of a point in the plane may be uniquely described by two coordinates. So for this purpose, we are using the rectangular coordinate system with origin O and two mutually perpendicular axes X and Y, which will pass through the O. And any point P...
Switch on your camera. Switch on your camera, show your face. Switch
Yes,
on
sir.
your camera and show your face. So all the contestants, please show your face, switch on your camera while presentation. Yes, please proceed.
Yes, sir. And any point P on the plane can be expressed either in rectangular coordinate xy or in polar coordinate r alpha, where r is the distance from the origin and alpha is the direction or the angle of the point. And in special case of the origin, r will be 0 and the direction will be undefined, that is alpha cannot be assigned. And it is easy to convert both polar coordinates into rectangular coordinates and vice versa. And this conversion is achieved using the trigonometric function sine and cosine. And the corresponding rectangular coordinates of P would be x is equal to r cos alpha and y is equal to r sine alpha. And this is the figure that is showing the relationship between rectangular and polar coordinates. Unfortunately, however, usual statistics like arithmetic mean and standard deviation, which we employ in linear statistical analysis, fail to have this required rotational invariance. We are forced to seek alternate statistics for describing directional data. So to address this issue, each observed direction is represented as a unit vector in the plane, and by summing these unit vectors, we obtain a resultant vector. The direction of this resultant vector gives an appropriate measure of the mean direction for unimodal circular data, while the length of the resultant vector indicates the degree of concentration of the observations. That is, directions that lie close together produce a longer resultant, whereas widely dispersed directions yield a shorter resultant. Now, coming to circular distribution, a circular distribution is a probability distribution whose total probability is concentrated on the circumference of a unit circle. And each point on the circle will be corresponding to a direction, and the probability associated with that point represent how likely that direction is to occur. And the range of the circular random variable theta, it can be expressed in radians, can either be from 0 to 2 pi or from minus pi to positive pi. And circular probability distributions can be discrete or continuous. And in all cases, it should satisfy the property xw is equal to x mod 2 pi. So Levi in 1939 has introduced this wrapping technique. And the technique that he has used is any linear random variable x on the real line can be transformed to a circular random variable using using theta is equal to x mod 2 pi. And this will correspond to wrapping the real line around a unit circle so that the probabilities at x is equal to theta, theta plus or minus 2 pi, etc. are all accumulated at the same angular position on this circle. Since this model operation is a many-to-one mapping, several values of the linear random variable x...
More than 40 slides, and we have only less than 10 minutes. Make a note of it.
Yes, sir. So this is the PDF of the wrap density function, which is given as in equation number 1, and the CDF as in equation number 2. So by this technique, both discrete and continuous wrap distributions are constructed. And this is the condition which is required, which should satisfy for a wrap distribution. Now, I'm talking about a truncated distribution, and the PDF of the truncated distribution is given as in equation number 3. And this is how the PDF can be represented, and the CDF is also given as in equation number 5. The main objective of this work is to develop and improve a baseline distribution for modeling circular data called the double truncated wrapped exponential distribution using the truncation technique. So this truncation mechanism is particularly useful when the observed circular data excludes certain angular regions or when some directions carry little meaningful structural information. So by strategically removing or downweighting these neutral or non-informative angular segments, the new distribution provides a more accurate representation of the dominant directional tendency in the data. So the PDF and CDF of wrapped exponential distribution, which was originally introduced by Jamilamedka and Kosubaski, is defined as in equation number 6 and 7, where lambda is greater than 0 and theta element of 0 to 2 pi. Now, this study aims to construct a more flexible distribution compared to the wrapped exponential distribution, making it suitable for improved modeling of circular data. So by incorporating the equations of 6 and 7, we are obtaining the DTWE distribution, and the PDF and CDF are given as an equation number 8 and 9. Now, the figure 1 is representing the linear plots of the PDF and CDF, and figure 2 is representing the circular plots for the PDF. And we have also studied some mathematical properties like the characteristic function. So the characteristic function of this distribution, of a circular distribution, can be obtained by phi of p, which is expectation of e raised to I p theta, where I is root of -1 and p can take only integer values. And that can also be expressed in an alternate way, which is alpha p plus I beta p, where alpha p is the expectation of cos p theta and beta p is the expectation of sin p theta. So the p trigonometric moment for the proposed distribution is given as an equation number 10. And the non-central trigonometric moments are given as 11 and 12. And now we are moving on to the location and dispersion properties. The mean direction of the distribution is represented by mu p when p is 1, while the mean resultant length rho p at p1 quantifies the concentration of circular data around the mean. So a higher mean resultant length that is closer to 1 indicate more data concentration towards the mean. And mu p and rho p can be computed using these equations. And substituting these values will obtain the 13 and 14 equations. And the mean direction and resultant length, that is mu is equal to mu1 and rho is equal to rho1, is calculated using these. We have also found the circular variance and the circular standard deviation, which is given as these equations. Now, the central trigonometric moments of the distribution are also expressed as alpha p bar and beta p bar, which is represented as equation number 15 and 16. The condyle function is also found out as in equation number 17. We have also found the skewness and kurtosis. So the skewness coefficient eta 1, which is a measure of asymmetry, is expressed as an equation number 20. And the kurtosis coefficient eta 2, which provides the insight into the peakedness or tail behavior, is defined as eta 2 and is expressed as an equation number 21. Now the table 1, it will provide the estimates of these coefficients and other characteristic features of the DTWE distribution. So as theta increases, the data becomes more symmetric and concentrated around the mean direction. So this is indicated by the decrease in coefficients of standard deviation, circular variance, and kurtosis. And simultaneously, the resultant length will increase with higher values of theta. This is the table 1. Now we'll move on to the application part. So to illustrate the effectiveness of the proposed model, we are analyzing a dataset from Krumbane, which is recording the directional measurements of 100 washout pebbles, which is collected from an outwash terrace along the Force River. And these directional measurements of these pebbles helps to reconstruct the past glacial meltwater flow during the late Wisconsin glaciation. So this information is vital for understanding sediment transport dynamics and the depositional environment of the region. So for comparative purposes, table 2 is providing AIC, BIC, AICC, CAIC, HQIC, and KS values for the proposed distribution, wrapped Agash, wrapped Shanker, wrapped Lindley, and wrapped exponential distribution. And as you can see, based on table 2, the DTWE distribution is achieving the lowest, as you can see in the first row, it is achieving the lowest AIC, BIC, etc.
Alicia Matthew, you have 2 minutes.
Yes, sir. So this is the circular Rosa diagram of the data, and this is the theoretical PDF fitting. Now, conclusion, this research emphasizes the role of circular statistics in analyzing directional data, showcasing its advantages over traditional linear methodologies. By introducing a novel circular probability distribution tailored to the characteristics of angular data, the study enhances the precision of ecological and geological analysis. And the findings demonstrate that the proposed circular distribution provides a superior fit for the outwash pebble dataset compared to existing models in the literature. And the new distribution will provide a better fit and more flexible model in comparison to other competitive distributions. And these are some of the references that I have used. Thank you.
Congratulations, Alicia Matthew, for completing it too early, giving more time for interaction. Now it is time for interaction. Professor Ghosh, Madam Jain, Kanjan Jain, ma'am.
Dr. Elisa,
Yes,
you
sir.
started with the cyclic distribution and then discussed the W truncated wrapped exponential distribution with single parameter. Why it is so? One question. Second question, you obtain the characteristic function of W truncated wrapped exponential distribution, not the moment generating function. Why it is so?
So for circular data, we'll be there is no moment generating function there. We'll be finding the characteristic function, and from there we are finding
You have to explain that part now.
Sorry, sir.
You have to explain. So in the beginning, you should have explained that MGF is not existing, so we are going for the CGF.
Oh, yes, sir. Sorry, sir. Yeah.
And second question, you started with the cyclic distribution, but you discussed about the doubly truncated wrapped exponential distribution with single parameter. Do you know about the cyclic distribution?
Sorry, sir.
No, you started with cyclic distribution, okay, but you discuss about doubly truncated wrapped exponential distribution with single parameter. Your discussion is on that part, not the cyclic distribution.
Sir, I'm sorry. I was not able to understand your question.
Okay, thank you.
Well, madam?
Yes, sir.
Yes, sir.
Alicia, can you explain me what is circular rose diagram telling you?
Yes, ma'am. So just like how a linear histogram is, we are wrapping that linear histogram onto a circular figure. So it's just like the histogram itself, but it will be like in a circular way. That is a circular rose diagram.
So can you conclude something from here? How do you conclude?
So we can know that these the values are from which like the values will be tending towards which area.
Like the first fan, you can say. First
yes, ma'am.
part.
Yes.
Which is pointing towards 0.
Yeah.
So those values are going in that region, 3 pi by 2 to 0?
Yeah. Yes, ma'am. So we can say that from pi to 3 pi by 2, there are no values. But all the other values...
Why there are no values?
The data is like that, ma'am. That's why.
No,
so if I'm having...
is the degree. 0 is not
yes,
the
ma'am.
number of
There's the
values.
direction.
It's not the number of values.
No, it's the direction, the angle. The angle
yes.
of the data set, yeah.
Angle of the data set.
Yes.
Actually, yes. Just 1 minute, sir. You are using these AIC, BIC for comparison purpose.
Yes, ma'am.
So do these AIC, BIC work for wrapped distributions as well?
Yes, ma'am.
For comparison, you used AIC and BIC. There are no other concepts?
No, ma'am. Till now, in all the other papers, we are using these AIC, BIC, and the case stat values. These
what
are the
CAIC?
goodness of the test.
What does CAIC stand for?
Consistent AIC, yeah.
Okay, thank you.
Well,
yes.
Alicia Matthew,
yes, sir.
You used, when Professor Ghosh asked about that moment generating function you did not talk about, you said that has it not been defined or it doesn't exist?
So as far as I know, all the papers have done using the characteristic function only. I have not.
You are a researcher in this circular data, and you must be knowing that what is the reason for not studying the moment generating function. Rather, you study the characteristic function. Okay.
Yes, sir. Yes, sir. Yes, sir. I will look into it.
Another point for comparison purposes, for comparing the properties of the estimators. Here, what properties you study for the estimators? In linear data, we study the unbiasedness, consistency, kind of a thing. What kind of properties you study, you discuss for circular type data, circular type distribution? I mean,
so we can conduct a simulation study and then we can prove the consistency using the.
Aren't there any theoretical concepts to make comparison rather than this computation alone? And all the computational tools we have used have been developed for linear data, particularly the Akek information, not about the other one. Kalmar-Smirnov and Akek information, Bayesian information criterion, all these have been developed for linear data.
Yes, sir.
Can you tell me what is the reason?
So I'm sorry, I'm not sure.
Okay, right. Thank you. Thank you for your presentation. Nice presentation. Congratulations.
Thank you, sir.
Well, our sir, shall we call the next candidate, the Swapna?
Yes, sir.
You are present. Please switch on the camera and share your screen.
Okay.
15 minutes presentation. 15 minutes presentation, 5 minutes interaction.
Okay.
Accordingly, manage your time to share your screen, to describe your screen.
Is this visible, sir?
Yes, visible.
Okay. So good evening, everyone. Myself, Swapna. I'm a research scholar from Department of Statistics and Data Science, Christ University, Bangalore. My presentation title is Shrinkage Estimation of the TTT of the Lomax Distribution and a Progressive Type 2 Censoring. This paper is done under the guidance of Dr. Jeevanand S. So this is the outline of this paper. So on this study, we focused on estimating the shape parameter of the Lomax distribution used progressive type 2 sensor sampling within the framework of string gauge estimator method. So string gauge estimators are derived based on both constant string gauge factors and weight factors under different weight functions which depend on the sample size, bias and variance of the base estimate used for string gauge the current estimate. So also we done the Monte Carlo simulation study at the last of paper. So Lomax distribution, which is a long-tailed distribution, and Pareto type 2 distribution, which is used as an alternative to the exponential gamma and Weibull distribution for heavy-tailed data. And the Lomax distribution is considered as an important model of lifetime model since it belongs to the family of decreasing failure data, and which is one of the well-known distribution that is very useful in many fields such as engineering and reliability and life testing. So the probability density function of Lomax distribution, which is given in the equation 1 and 2, where theta and lambda are the shape and scale parameters respectively. So total time on time graph has gradually become a crucial empirical and scale invariant graph of all tools used in reliability analysis, not originally designed to be used in failure analysis directly, but the plot is the key to working with failure data, and it is also the counterpart, and it extends its applicability across novel domains in reliability and econometrics. And it is more related to Lorentz curve. So for the above model, the TTT simplifies to equation 3. So this paper is estimated to estimating the scaled TTT transform for the Lomax distribution and the progressive type 2 censoring. At this end of the paper, improving the application of reliability analysis based on the results of the provided distribution by offering more versatile and efficient methods for analyzing survival data. So in conclusion, the TTT transform can be used as the starting point of the reliability analysis because it is simultaneously situated at the theoretical and practical levels, and it is applies to analysis beyond the discipline and demonstrates further versatility in different estimation methods. So progressive sensor scheme, we estimate DTT based on progressively type 2 sensor scheme. The first failure is observed as R1 of the surviving units are randomly selected and removed. At the second observed also selected R2 and the surviving units are randomly selected and removed. And this experiment is stops at the time when the Vth failure is observed and the remaining will be RV equal to N minus R1 minus R2 up to RV minus 1 minus V surviving units all are removed. To getting more information about progressive sensor schemes, we refer this much of papers. So the likelihood function corresponding to the setups can be written as equation 4, where mu is already defined, and substituting the density function of Lomax distribution 1 and 2 in the above likelihood function, we got the likelihood function as equation 5. So assumed that lambda is known and differentiate with respect to theta and equating to 0, we obtain the estimates as theta cap in equation 6. So this estimate theta cap is substituted in the DTT form. We got phi cap of t, which is as equation 7. So shrinkage estimator, which is introduced by Thomson, and shrink raw estimates like the maximum likelihood estimator toward prior information using a shrinkage weight factor, and which these estimators have been extensively studied in Bayesian context, particularly in reliability applications for exponential distributions. For getting more information about shrinkage estimators, we used these much of papers for referring, and the estimate is equation 8, where alpha is the shrinkage weight factor. So we consider the three shrinkage weights are equation 9 and substituting these values of theta cap SH in the equation of the phi cap of SH of t, and we got the equation 10 as this. So simulation study, the whole simulation study was conducted using Python, and which is involved generating 1000 replicated datasets for different sample size. We generated the sample size of n with a 10, 20, 50 were generated from the Lomax distribution with the different theta values 1.5, 2.5, and 3.5. And we proposed the shrinkage estimators and maximum likelihood estimator and computed the bias MSE and RE, and the steps 1 and 2 were repeated 1000 times for each combinations of n and theta. So we calculated the bias and variance, MSE and relative efficiency also. So this is the first table, which is progressive sampling scheme. As I already mentioned, the first sample is taken as randomly selected.
Your screen is not visible.
Sorry, sir.
Your screen is not visible. Yes. Table 1 appears.
Okay. So this is table 1, progressive sampling scheme. Where first sample is taken as randomly and it is removed, and second sample also taken randomly and just removed, and up to RV, which is RV equal to R1 minus R2, R1, R2, up to RV minus 1 minus V. Then this is table 2 for estimates for NV with a 10 sample size and 20 and for 50 also. So from these tables we observe if it is smaller theta values, it will be tend to higher bias and MSEs, and if it is larger theta values, which introduce the lower bias and MSE. So as the sample size n increase, bias tends to stabilize, but this effect is more noticeable for smaller theta values. For larger theta values, the bias remains problematic even for larger sample sizes. So these results across all three tables show the shrinkage estimators consistently outperform the MLE in terms of bias and MSE for different sample size combinations and theta values. As the sample size increase, both bias and MSE decrease for all methods, confirming estimator consistently. So among the shrinkage methods, SS3 often achieves the lowest MSE and highest relative efficiency, especially at a higher theta value. So this suggests a adaptive shrinkage improves estimation accuracy and reliability, making it a strong alternative to traditional MLE, particularly in small or moderately sensor samples. So conclusion, the simulation study confirms that shrinkage estimators significantly outperform the classical MLE in terms of bias, MSE, and relative efficiency. Among the proposed methods, the shrinkage estimators consistently delivers the best performance, especially as sample size increases. These findings highlight the practical value of shrinkage techniques in improving the estimation accuracy and robustness, particularly in scenarios and small sample size also. So these are the references. Thank you.
Well, congratulations. You are well before in time. So within 8 minutes, you completed. And sir, Madam, Kanjan Madam?
Yes, sir.
And Swapna
She has been very quick.
Time for interaction.
Sorry, sir. Professor Ghosh, you can go ahead.
Sir, Professor Ghosh, sir.
Congratulations, but I didn't find any good results on this your case. Just to you have aim was to estimate total time on time for transforming for Lomax distribution. This is you have started. And you use the Emily method, actually shrinkage method. Always you use to find the bias and reduce the variances. And our idea here is such a way that at least one of the beta parameters must be not exact to zero, but near to zero. Very near to zero. This is the exact idea of the shrinkage estimator. But this I didn't find any activity like that. So what we want to say is it was difficult for me to understand.
Sorry, sir, what?
Then what we want to see, what you estimated, only you are telling that as that n decreases, theta also decreases. This is only result I found from you, nothing else here.
Actually, we have used Lomax distribution just because of it is long-tailed distribution. So when we calculate this, when we apply the shrinkage estimators, we get the bias and MSE as lower, and we will get the reliable results.
The last question, you have used shrinkage estimator. Can't you use the lasso estimator?
Lasso estimator, yes, sir.
What is difference between two estimators?
Actually, we have planned to make another paper with along with this paper, just like penalized estimation. Just sir, you already told lasso type penalty and quadratic penalty.
Yeah. Thank you.
In penalized estimation, we just giving the penalty term, which might just like minus lambda g of theta, and we took g of theta as theta square by 2 and the absolute value of theta also. In this paper, we just string the some elements to the already existing maximum likelihood to get the reliable results.
Okay, thank you.
Madam?
Okay. Ms. Swapna, I think I share the opinion of Professor Ghosh. Okay, I didn't find much content or theoretical content in this paper. I don't want to discourage you. You can do more work in this direction. Presentation was good. Congratulations for that. But again, my question is, why did you go to shrinkage estimation?
Sorry, ma'am.
Why did you go to shrinkage estimation? Give me just one solid reason.
Actually, if it is smaller sample size, it will give the reliable bias and MSE, and it will give the more efficiency when we use the shrinkage estimates. If it is smaller sample size, but we are not avoiding the larger sample size. But if it is smaller sample size, we will get the reliable variance and less bias. So that's why we use shrinkage estimates.
But why did you think of going for this shrinkage estimation? Was it just to produce another paper, or there was some particular reason? You said it increases efficiency. But there must be some basic reason. Why did you go to shrinkage?
Actually, when we do the simulation study, always eliminating the small sample cases, we always prefer to use larger sample cases. So if we use small sample case, when we use the shrinkage estimates or penalized estimation, we get the information about what will be happen if it is small samples, or it will be reliable, or if we get any reliable results, just like that.
Okay, thank you.
Well, Swapna, of course, I congratulate you for becoming a contestant to the final round. What practical real data you have taken for the study?
No, sir, just to use a Python for randomly generated.
No, for the simulation studies are useful for making some conclusions about the behavior of the estimators and so on. But you can also explore the application of your results for real situations. You could have taken your real data, because nowadays it is not at all difficult to find data for carrying out, for applying our research results. So you should try for applying your results for real data. This one,
Okay.
right? And what made you to think about in what way your maximum likelihood estimator you thought that it is not so suitable, so that you have moved on to shrinkage estimator? Do you have any specific reason for moving towards shrinkage estimator than maximum likelihood estimator? Because you have taken maximum likelihood estimator as a competing estimator, right?
Yes, sir.
Is there any specific reason?
No, sir. When we're using maximum likelihood estimator, it will give the higher bias and variance. So when we apply the shrinkage estimates, it is lower bias and MSE, and the results will be reliable.
Can you tell me can you explain with the behavior of the likelihood?
Behavior of likelihood. Sorry, sir.
Okay, right. So, okay, right. Sir, there are, of course, since we have time, we can also invite one quick question from the participants.
Hello, Swapna. I have a doubt regarding your table 1. Can you just please go back to the table 1 where you mentioned the progressive census schemes? Swapna, your screen is not visible actually. I'm not getting
I'm trying, sir. Just
Okay, please.
now is it visible, sir?
Yeah, it is visible. Can you please go to that slide where you mentioned that progressive census table?
This one,
Yeah,
sir.
yeah, this one. So here for the first one, you considered n equals to 25 and v is 18, right? So
Yes, sir.
what is the difference between n and v?
Actually, n is the sample size 25. V
Yes.
is the randomly taken by using the
Yes.
progressive sampling scheme.
Fine. Yes,
So,
fine.
suppose if we take the R1 as the first sample and
What-
selected and deleted it randomly, and suppose if we want R2, then take it randomly. Suppose
So,
we want to.
see. What is happening here? Like you are consider R1, R2, R3, R4. What about these values? R1, R2, R2. These are the random removals, right?
Yes, sir. Yes, sir.
Yeah. See, one thing is that in case of progressive sensing scheme, the number of random removals, the sum of the number of random removals, and whatever the value you have taken here, v, that should be equal to the value of n, and it is not matching here. So I'm just worry about that table actually. Okay, and please go through the progressive census schemes, some of the basic papers related to that. Professor Kundus, a lot of papers are there in this field, so you just need to go through that. Okay, I think your census scheme is not written here properly.
Okay, sir.
Okay.
Well, thank you, Dr. Subhagan Datta, and thank you,
Yes.
Swapna. You can,
Thank you, sir. Thank you.
Thank you, sir.
okay, right. You can close your screen. Let us invite the next contestant, who is Dr. Mohammed Amir.
Yes,
Share your screen. Start presentation. 15 minutes presentation, 5 minutes interaction.
okay, thank you. Good evening, sir. My name is Mohammed Amir. Today is my presentation on the topic of estimation and prediction for Lomax relay distribution based on record value using an application of rainfall data. These are my outline, and my paper abstract is this paper focus on estimating parameter from the Lomax relay distribution using upper record data through maximum likelihood estimation and Bayesian method under different loss function, and we find exact and credible and confidence interval, and we predict the future record value of Lomax relay distribution using a record data through a classical and Bayesian approach, and we fit a real life data from rainfall data from Minneapolis, St. Paul. And record value arises naturally in both theoretical and research practical application. They are used in hydrology and seismology, psychology, medicine, and in seismology, the importance of prediction of magnitude of earthquake that exceed all the previous records in a given region. Now, record value, the value of XJ is defined as upper record value or lower record value if all the preceding value are smaller or greater than Xi. This one is given by a Chandler in 1952. And Lomax relay distribution was given by Venegas in 2019. And this distribution is useful in survival analysis and reliability analysis and risk modeling, reliability engineering. And these are the PDF and CDF of Lomax relay distribution. And we basically, our paper is focused on estimation of parameters of Lomax relay distribution using record data. So we use classical and Bayesian approach to estimate the parameters. And we also estimate the parameter using a point and interval estimation by using a pivotal quantity, credible interval, and approximate maximum likelihood estimation. These are the joint likelihood. These are the likelihood function of upper record value, and we take a log, natural logarithm, both sides, and we take a differentiate with respect to theta and with respect to theta to find the MLEs of the parameters. But they are not in closed form, so we used optimum function in R to estimate the parameters by using the MLE. And we find the asymptotic confidence interval by using the log likelihood function to find the approximate confidence interval of the parameters by using a record data. And we also find exact confidence interval by using the pivotal quantity, which one is independent from free from parameters. And we take a lemma from Arnold et al. Which one is find by using minus ln1 minus fy, which one is complement of the CDF, and which one is free from parameter. And we found they follow the standard exponential distribution. And we develop a lemma. The first time record values from the exponential with parameter value, then spacing at t1, t2 minus t1, and up to tm minus 1 are IID random variable. Then they follow the exponential with parameter 1. Now we find the confidence interval by using the pivotal quantities. These are the estimation of alpha, and these are the confidence interval for theta, and they are in not closed form, so we used our unit root method to solve this confidence interval. Now we used Bayesian estimation to estimate the parameters, in which we use square error loss function and Linux and general entropy loss function. These are the Bayes estimators. And we used gamma distribution. We use a hyperparameter gamma distribution, which one is A1 B1, gamma A1 B1, and gamma A2 B2 for two parameters alpha and theta. These are the posterior density of the parameter theta and alpha by using the product of likelihood function and joint priors of alpha theta. And we used Markov chain Monte Carlo method to estimate the parameter, because they are not in closed form. One of the parameters, my theta and alpha, is found in closed form, but theta is not found in a closed form. So we used MCMC technique to find the posterior density and then estimate their parameters. These are the Bayes estimator of square error loss function, and this second one is for Linux, and third one is general entropy loss function. And these are the credible interval. These are the credible interval for parameter alpha and theta. And now we find the point prediction of future record value using a classical approach. These are the likelihood function of the class, which one is given by Vasak and Balakrishnan. Now we take the log likelihood function and then differentiate with respect to asset record, which one is not in closed form. So we find with the help of optim function in R to predict the future record values. And we also discuss interval prediction of upper record value using a pivotal quantities. We make a three prediction we obtain three interval. First one is case 1, second one is case 2, and third one is case 3 for alpha theta when both unknown. And first one is for alpha known and second one is theta record values by using a square error loss function, and second one by Linux, and third one with the help of general entropy loss function. And these are my simulation studies as given in table 1, in which we find some pattern. Basically, when we increase the record value, then their MAC decreases, and their MAC decreases as the record value increases under all the cases. But we found Bayesian are good for small samples, in which their MAC always found smaller than the classical. And their credible interval are also for simulation studies for 3, 4, 5, 6 record at different level of confidence, 90% for 95% and 98% for alpha 0.9, and their record value increases, then width of the credible interval also reduces. And we fit a real life data application and analysis, in which we use rainfall data, and these are their data. And we plot a QQ plot and empirical CDF plot to show the best fit, and their p-value is also found to be 0.3929, which shows this data fit into Lomax relay distribution for record data. And we estimated these parameter using MLE, square error, Linux, and general entropy, and their exact and their credible intervals also. And we predict future record value, kth record value, that is fourth record values. And these are the second column is true value, and this one is predicted by using a maximum likelihood predictor, and fourth column is using a square error loss function and Linux and general entropy loss function, in which we found the square error loss function, which shows minimum root mean square error. It shows this one is best. Square error prediction of future record values is based under the square error loss function, because their root mean square is smallest among all. And their prediction, upper and lower prediction bound, by using it, we developed the three cases of record values prediction interval. This one is first one, this one is second one, and this one is third one. And their width are also given in there. In third case, smallest width are found, which one is best for my real data. Said conclusion, these studies developed an extensive framework for estimating the parameter of the LR distribution and predicting for the future record value using upper record. And Bayesian approach perform better than the classical approach in terms of MLC when both approaches are implied. A similar simulation studies confirm the consistency and efficiency of the Bayesian approach. Point prediction performance is enhanced under the Bayesian framework, the square error loss function yields the most accurate result. A non-Bayesian approach was developed to interval prediction using a pivotal statistics. Three predictive intervals were obtained, in which the third provided the smallest, which indicated the most precise prediction. Credible interval for both parameter reduce in length as the number of record increases. This demonstrates that the consistency and efficiency of the Bayesian approach, which shows the consistency and Bayesian of the efficiency. Finally, we applied a rainfall data to validate the suitability of the LR distribution. Both point and interval estimation and prediction are implied. Overall, the proposed theory offers effective tools parameter prediction in various fields where they have significant role. These are my references. Thank you.
Completing the presentation before time. Sir,
Mr. Ghosh.
My one question is that you have taken the rainfall data of USA, Minneapolis, and St. Paul. Why don't you take the rainfall data of India? We have just many states, Kerala, Assam, Bengal, etc., heavy rainfall. What is the reason of taking that data?
Sir, it is easily available in my supervisor research paper, so that's why, sir, we use.
If you have taken Indian data, it is helpful for our Indian government, na?
Yes, sir. Yes, sir.
The second question is, you have used so many methods of estimation, MLP, Bayesian, and MLE, so many loss function, square loss function, relax function. And finally, you are telling that square loss function giving the best prediction.
Yes, sir.
But what is the ground for that? How you can say that is square loss function giving best prediction for your rainfall data?
Because, sir, we found that the root mean square value is smallest among all the method. We have true value actually, sir, and we predict these value using under different method, and their root mean square value is smallest among all the methods. So that's why, sir.
But I found confidence interval of lower limit, upper limit has large difference. If lower limit is 1 point something, the upper limit was 15, 17 like that.
But, sir, we estimated by using the credible interval, sir. But this one is the prediction interval, sir.
Mm-hmm.
This one is the prediction interval of the record value, sir. But yes, sir.
Okay, thank you.
Madam.
Okay. Mr. Amir, you have worked on upper record values.
Yes, ma'am.
So those theorems, lemmas that you were showing, have they been proved by you?
Yes, ma'am.
Theoretically?
Yes, ma'am. This one is my research paper 4, and this one is my thesis work, ma'am. And I am pursuing PhD under the Dr. Hasi Vatar in Aligarh Muslim University.
Are there not results available for upper record values earlier in literature? How are your results different from those which are already available?
Ma'am, first one is I am working on different distribution, Lomax relay distribution, and most of the work does not work on record value because there is a very complicated WAM. But they mostly worked using order statistics. But I worked on record value to estimate and predict the future record value.
I think there is a lot of work on record values as well.
Yes, ma'am, but in Lomax relay distribution does not.
So this particular distribution has been handled by you.
Yes, ma'am. Yes, ma'am.
Another thing, when you were showing YMLP, estimate of YMLP, can you show me that table?
Yes, ma'am. Yes, ma'am.
No, previous one.
This one, ma'am.
Go to the
MLP.
back. Go to back. Sheet. I think there were more values of Y cap MLP. No?
This one, ma'am.
No. Y cap, not this one. Go ahead. Next. Go ahead. Maybe that table you were showing me. Just go. Okay.
Yes, ma'am. This one.
Why is there so much difference between true value and the estimator?
In maximum likelihood predictor, ma'am.
Yes.
Yes,
There's
ma'am.
so much difference.
Because, ma'am, this one is not for a small sample, ma'am. Because record values are very less, so it can be handled with Bayesian, ma'am. So the classical approach does not work for a small sample, ma'am.
So that's why this
yes,
even
ma'am.
in for fifth record,
yes,
this
ma'am.
is quite deviating a lot.
Yes, ma'am. For because we have only 55 records values, so that's why, ma'am. And Bayesian it could be handled very well for a small sample, ma'am. So that's
And did
why.
you use MCMC?
Yes, ma'am. I also used MCMC technique because one of my parameter are not in closed form, so that's why, ma'am, I used MCMC technique in
These figures.
Yes, ma'am. And this one is I'm showing, ma'am.
Yes, he has shown
Yes,
that
ma'am. This one is not.
Okay.
This one is closed form, and
Okay.
other is not in closed form. So that's why we use MCMC technique, ma'am.
Okay, thank you, Mr. Amir.
Well, Mohammed Amir, congratulations for carrying out work with the application of the Bayesian procedure. Two things I want to ask. You computed mean squared error. You compared the performance of a Bayes estimator with maximum liquid estimator. I saw that you computed mean squared error.
Sorry, sir.
You computed mean squared error for comparing the behavior of a Bayes estimator with the maximum liquid estimator?
Yes, sir. Yes, sir.
Oh, is it possible?
Yes, sir. Mean square.
No, the thing is, when you repeat the sample, non-Bayesian approaches, the model stand alone. Model will not change. Whereas in the case of Bayesian, once when you change the sample, the posterior will also change. The model will be totally different. So how can you compare, how can you calculate mean squared error? Because here in the case of non-Bayesians, the models are all same. Whereas in the case of Bayesian, once when you change the sample, the posterior will be different.
Yes, sir. Posterior will be different, sir.
How can you compare? How can you calculate the mean squared error for different models? Because mean squared error can be computed for different samples, but for the same population, same model. Base model shall be same. Because as far as Bayesian is concerned, you can compare the estimate. That's it. You can compare the estimate of Bayes estimate with the other classical procedures, not mean squared error. Okay. Another point, you showed the performance of Bayes estimator based on different. You computed Bayes estimator for different loss functions. Good,
Yes.
but the thing is, for every decision-making problem, there will be only one loss function that will be appropriate for studying the situation, right?
Yes, sir.
Can you deal with the squared error loss function, Linux loss function for the same situation?
Yes, sir. When
By that,
C value is equal to 1, then it will become same, sir.
No, the thing is, choice of loss functions. You are making a choice of loss function with reference to the Bayes estimator. Is it wise? Is there any reference for that? Did you see that? Please check it. Okay.
Yes, sir. Okay, sir.
Right. Thank you, Subhankar Datta. The time is already, we are crossing the time. So we do not have time to spare for the participants to ask questions. Now we will move on to the next participant. Satya Prakash Mishra, Mohammed Amir, you can close your screen. Satya Prakash Mishra, please share your screen and switch on the camera.
Is the screen visible, sir?
Yes, screen is visible. Please start your presentation.
Good evening, jury members and all the participants present here. So the title of my talk is Bayesian Inferential Procedures for Exponentiated Distribution under Adaptive Progressively Censored Data. I'm a research scholar in Department of Statistics, Central University of Haryana, under supervision of Professor R.K. Sahu and co-supervision of Dr. Manoj Kumar from University of Delhi. So title seems to be very much precise. We have to compare the different inferential procedures for the considered distribution under the censored data. This is the outline of the work. Here we have considered 4 methods, basically the classical estimation, Bayesian, expected Bayesian estimation, hierarchical Bayesian estimation, and then we have performed a simulation study to check out that which estimation methods performs well under the considered setup. Then we have also done the optimal censoring to check out which censoring scheme is more suitable and practical. And then the methodology is validated using the real data interpretation. So basically, in the live testing experiment, we all are familiar with the different censoring methods that are available in the literature. First of all, type first censoring, where we prefix the time. Then we move on to the type second censoring, where we prefix the number of failures. As soon as we get that prescribed number of failures, we stop the experiment. Then we move on to the progressive type second censoring experiment, where at each failure, certain number of units are removed. Then we moved on to the adaptive progressive type second censoring, where we introduce one more constant of time. This censoring scheme was basically proposed by Nag et al. In 2009, and after that, this censoring scheme have been well studied by various researchers, and I have mentioned some of them. Nag et al., first of all, in 2009, he has performed a statistical analysis based on the exponential lifetime under this censoring. Similarly, Mahmood et al. 2013 has used the similar this adaptive progressive type second censoring scheme. So if we move on to this censoring scheme, so this is the schematic diagram of adaptive progressive type second censoring. Here we can see that at first failure, R1 units are removed, and at X2 failure, R2 units are removed. Similarly, this experiment proceeds. If we get the prefixed M number of failures before the considered time T, it basically behaves as the progressive type second censoring. But suppose we did not get the prefix number of failures till the time T, then what it after does, it does not remove any live units from the experiment, because as soon as we have more live units, we will get the most chance of getting the failures. Then at the end of the experiment, all the units are removed. That is n minus summation equal to 1 to j ri. So this is the basic idea of adaptive progressive type second censoring. Then here we have considered the various methods of estimation available. First of all, maximum likelihood estimate. This is the prominent classical method of estimation available in the literature that we have used since very long time. Then another method that is considered here is Bayesian estimation, which incorporates the prior knowledge into the knowledge that we have available to form the posterior and get the estimates from that. Then there one more estimation method, that is Bayesian estimation method, which was developed by Han and Ding in 2004. After that, various studies have been performed on this. This estimation method, what it does, it gives the distribution to the hyperparameter of the prior. Then after that, we have the hierarchical Bayesian estimation. This is the most basic idea which was proposed by Lindley and Smith in 1972. This idea we have used for getting the estimation by using the hierarchical modeling techniques. Here, what we have performed, we have generated the posterior by making the 2 stages prior, which makes the method more reliable and robust, because it develops the prior in the 2 stages. There are various research have been done on Bayesian hierarchical Bayesian, Okasa, Han in 2017 and Gupta 2017. And the Han, the researcher, he has done various works on using the Bayesian and hierarchical Bayesian techniques. So here what we have done, till now, hierarchical Bayesian techniques had not been discussed using the 2-parameter setup. Most of the research have been done using the single parameter. So here we have tackled both the parameters for the hierarchical Bayesian estimation. Now the move on to the distribution that we have considered. We have considered the well-established inverted exponential distribution, as Gupta in 1998 had developed the family of distribution. After that, exponentiated family has been well established and exploited by the researchers. So here we have considered the IED. Equation number 1 and 2 represent the CDF and PDF of the distribution. Here alpha and lambda are the shape and scale parameter. This distribution is widely used in practical scenarios also, as this distribution introduced by Abema Al-Sekti in 2009 as a generalized case of one parameter inverted exponential distribution. This distribution also exhibits the increasing or decreasing hazard rate function, making it suitable for the analysis. And IED is also a special case of exponentiated Wsta distribution, and we can 3. Then we move on to the classical estimation techniques. So first of all, we have formed the likelihood, which was described by Naik et al. In 2009, in which he has addressed the idea of adaptive progressive type second censoring. So equation number 3 represents the general likelihood. Then by putting the PDF and CDF into the equation number 3, we have got the likelihood function in the equation number 4. Then this is the basic general technique that we have studied to get the log likelihood function. We have generated the log likelihood function by taking log. Then we have to solve this equation. So but we have taken the derivative with respect to alpha and lambda. Then we have to solve this two simultaneous normal equations for getting the estimates. So these two normal equations are not in the closed form. So we have used the Newton-Raphson technique to get the numerical solutions using the R software. Then we move on to the Bayesian estimation. Here we have assumed the gamma prior distribution for both the parameters alpha and lambda that has been represented in equation number 6 and 7. Here A1, B1, A2, and B2 are the hyperparameters. Then using the prior and the likelihood that have been mentioned previously, the joint posterior have been developed for the parameters alpha and lambda in equation number 8. Then we have considered two loss functions. One is symmetric, that is square error loss function, and asymmetric, that is general entropy loss function. As when overestimation and underestimation are of equal importance, then we can move on to the symmetric loss function. And when overestimation is more serious or the underestimation is more serious, then we can move on to the asymmetric loss, in which most established is general entropy loss function. This was given by Calabria in 1970. Then we have obtained the Bayes estimator under both the square error loss function, which is self and jelf, in the equation number 9 and 10. So from here we can see that these equation number 9 and 10 cannot be solved analytically. So here also we have used the MCMC techniques, and in the MCMC we have used the Metropolis-Hastings technique to get the estimates out of these equations. So here I have mentioned that we have used the MCMC techniques to solve these integrals, and we have used the conditional posterior to generate samples from the to get the samples for alpha and lambda in the equation number 11 and 12 shows the conditional posteriors. Then we moved on to the another estimation method, that is E-Bayesian estimation method, which is basically expected Bayesian estimation. Here, but it was idea suggested by 1997 in the Hahn paper. He has taken the suppose we have two hyperparameters as A1, B1 and A2, B2. So you have to choose in such a way that the prior should be a decreasing function of alpha and lambda. So by making this setting, we have taken the hyperparameters A1 and A2 between 0 and 1, and we have defined some upper bound B1 to C1 and B2 to C2. So here what we have done, we have made 3 distributions for alpha and 3 distributions for lambda. This is described by 1, 1, 2, and 1, 3. Then making use of this next level distribution, we have got the E estimates using this. Here the E-Bayes estimates under self is given by the expectation, and the E-Bayes under jelf is given by the equation number 16. Then making use of MCMC method, we used to solve the equation through the R software to get the expected Bayes estimates. Then we moved on to the another hierarchical Bayesian estimation setup. Hierarchical Bayesian estimation setup is based on the 2-stage prior specification. In the first stage, we have taken the gamma prior. In the second stage, we have taken the equation number 13 and 14. This is the second stage prior. Then merging these two prior, we have got the joint prior, and then we have formed the posterior. This is represented by the equation number 20, 21, and 22. Then out of these 3 posteriors, we have generated the samples, and then we have calculated the H-Bayes estimates. So for alpha, this is the posterior 20, 21, and 22. And for the lambda, this is the hierarchical posterior density function for lambda given by 26, 27, and 26. These are 6 hierarchical posteriors. These are the hierarchical Bayes estimates for alpha and lambda based on squared error loss function, and hierarchical Bayes estimates for alpha and lambda under general entropy loss function, which is represented by question number 29 and 30. The integrals presented is here 29 and 30 cannot be solved directly. So for the same reason, we have employed the MCMC technique to solve the equation through the our software to get the hierarchical Bayes estimates. So basically, now moving on to the simulation study that we have performed, we have considered 3 censoring schemes: left, right, and a uniform censoring. And for the degree of symmetry of the loss function, we have taken delta is equals to 0.5, accounting for the overestimation, and delta is equals to negative 0.5 for the case of underestimation. The upper bound of the hyperparameters B1 and B2 has been taken as C1 is equals to 2 and C2 is equals to 3, respectively. Now, if we move on to the simulation study, so general discussion have been made here that from the simulation study, we can see that as the sample size n and the number of observed failure m increases, the estimated value converges to the true value, and the MSE progressively decreases for all the obtained estimators. Based on hierarchical Bayes estimates, the showed here inequality. The alpha hat HBGI means hierarchical Bayes estimates under GELF for both alpha and lambda has the least MSE. Similarly, we have also calculated the, and also the one more thing, the value of T increases, the MSE of all the estimated also decreases. Means as the value of T in the adaptive progressive censoring setup, as the time increases, the MSE of all the estimates decreases. This is a general trend, because as the time increases, the censoring schemes more goes to the progressive censoring setup. This trend can be described from that reason. Then we have also calculated the confidence interval in the classical setup and the credible interval in the Bayesian setup. As the sample size is less, so we have also calculated maximum likelihood estimates and MSE of alpha and lambda for fixed value of alpha is equals to 1.5 and lambda is equals to 2.5. So from here we can see that as the T increases, the MSE also decreases, and as the sample size, effective sample size n and m increases, the MSE of both the parameters alpha and lambda tends to decrease. Then we move on to the table. This table is quite long, seems to be. So here we have discussed the Bayes, E-Bayes, and hierarchical Bayes estimates along with their mean squared error. So here from we can see that as the sample size in that is 20 and 8 and 30 and 12, as the effective sample size increases, the MSE of all the estimates tends to decrease. And the estimates that have been mentioned here tends to converge to their true values, as we have considered here 1.5 and 2.5. And here for the degree of
2 minutes.
censoring scheme is more suitable and practical. So there are 2 methods that is described in the literature, that is minimize trace and minimize and determinant, to check that which censoring scheme is more suitable. So from here we can see that using for the small sample size, optimal censoring scheme is first. Trace and minimum determinant. The adaptive progressive type second censored sample from the real data analysis. And we have the adaptive progressive type second censored sample from the real data analysis. And we have also taken that same delta is equals to 0.5 and negative 0.5. And now
time is over, Satya Prakash Mishra.
Then sir, ML Bayes estimates have been obtained for the ACT dataset and shows that all the methods have shown the similar estimates. Then we have also taken the average length of ACT dataset, and from here also we can get the similar results, that average length of all the estimates tends to decrease as the sample size increases, and here also the SPD interval has the least length, showing the similar results that have been shown in the simulation study. So basically we can use the H-Bayes estimates can be used for better results as compared to the E-Bayesian hierarchical Bayesian setup. These are the references.
Okay, right. Thank you. Professor Ghosh, Madam Kanchan Jain.
Yes, sir. Okay.